Okay.
Let's begin. Picking up where we left off. So last time we did everything I wanted to say about composition of functions, so now we're going to talk about inverse functions. Let's do that. So let f be a function. If it's inverse relation, because remember a function is just a relation. If its inverse relation is also a function, let me give it a name. If its inverse relation g is also a function, and you call f invertible. And g the inverse of f. And write g equals f below dash minus 1. Same notation we use for when we're talking about inverse relations. This relationship is of course symmetric. I mean, if you take f inverse and you get g, then if you take g inverse, you will get f. So this will work in both ways. But it turns out that if you take the relation that describes a function and you swap all the first and second coordinates, if that thing is also a function, then we call this its inverse. So let's give an example here. Say A is A, B, C. B is 1, 2, 3. Let f be the function. Just straightforward. Say A goes to 1, B goes to 2, C goes to 3. Let H be a function. A goes to 1, B goes to 1, C goes to 1. Then we would take the inverse relation of f. We would obtain 1 goes to A, 2 goes to B, 3 goes to C. Note then that this is a function from B to A. So we can call this inverse. So this function f is invertible. We can find its inverse. The function h, though, if I take the inverse relation of h, that would be 1 goes to A, 1 goes to B, 1 goes to C, and this is not a function. Because not all the domain elements appear. It's not even a function with a restricted domain because we have the same guy go to potentially different guys. So that's not a function. Here h is not invertible. So we want to be able to look at the inverse relations and see if those are functions. If that is the case, the function is invertible. And the inverse relation is also a function in its own right that we call the inverse of f. And of course, if g is the inverse of f, it means that f is the inverse of g, and by the same reason. does an inverse function exist? Theorem. F from A to B is invertible. If and only if. Does everyone know?
What's one?
F is
Bijective.
bijective. It has to be both. This is one of the reasons why a bijective function is an important kind of function. It can tell us when an inverse will exist. And sometimes we want to be able to talk about the inverse. We want to know which input did a given output come from. It's good practice to try to prove that yourself. I'm not going to actually prove it. But we can actually take that as somewhat of a definition. We know that every bijective function will be invertible, and every invertible function is a bijection. And you would have done that in pre-calc, maybe calc 1. You would have been given some arguments as to why that is. But now you can actually prove it in a lot more rigor. We're not going to do it though. You can even add to this, even though it's because this relationship is symmetric. It stands to reason that the inverse is also bijective, just something that you should be aware of. So if a function is bijective, it has an inverse, and when you find its inverse, that function itself is also bijective. Here's another classification that we have, and we'll probably prove this one. So f is a function from A to B. G is a function from B to A. If f composed with G is the identity on B, and G composed with F is the identity on A, then F and G are bijective, and G will be the inverse. So you might have seen this in familiar terms where back in Calc 1, or even earlier, where they said if f of g of x is x and g of f of x is x, then f and g are inverses. This is somewhat of an abuse of notation. It only works because at this level, your sets were always sets of real numbers. So they could use x to represent both of them. They didn't have to identify where this x actually lives, because we know it lives in the real numbers. But to be specific, it has to be the identity on a special set. So if you're looking at things that are two different sets, this could be a set of letters, that could be a set of numbers, then in here, this must give you the identity function on the set of numbers, this must be the identity function on the set of letters. So there's a little bit more nuance in the relationship. But this is kind of the idea that you would have seen before. We just need to be a little bit more specific for the general case. Let's prove this. And after that, we will prove, we'll do a specific example of a specific function. And then we'll move on to permutations, which we're only going to touch on that, just a splash. You'll do a lot more on that in abstract algebra, and then we will move on to chapter 10. We'll start to talk about the cardinalities of sets. Okay. So go. What do you think we need to do now? So we're going to make this assumption. And we need to show that these two are bijective, and one is actually the inverse of the other. Of course, this relationship is symmetric. Without loss of generality. Let's just tighten this up a little bit. We show F is bijective. So showing that G is bijective will be a similar argument. So let's just focus on the F. So we need to show F is 1 to 1 and F is onto. How do you know F is 1 to 1? What do you need to show in order to show that F is 1 to 1? What do you need to show here?
For any two images under F that are equal, how do you say this? For all,
If f of x is equal to f of y, then if f of a is equal to f of b, then a is equal to b.
Okay. Let's show that. These are things we need to know. We need to know the definition of the things that we need to show. Okay, so how are we going to do that? So now assume f of a equals f of b. Right? Obviously your a and your b are in the domain A. Okay, so what can I say now? Huh? How would I be able to say that a equals b? I literally don't know anything about this function. I don't know its definition, how it's defined, if it's a polynomial, if these things are letters or numbers.
can you plug it in somehow to the
Plug it in where?
the composition?
Which composition? What I would do is I would plug into this composition. Let's see. This would mean, since those two are the same numbers, I will get the same result if I just plug those in here. Why? Because the function is a relation such that each result so I can throw them both into G, I get the same thing because I'm plugging in the same element. But what is G of f of a? That's just a. Because G of f is the identity on a, so if I plug in an element that's in a into G of f, it gives me that element back. That was the definition of the identity function. And G of f of b is actually going to be this. Since G of f is the identity on a. So f is 1 to 1. How do we show that f is onto? What do we need to show to know that f is onto?
For all b,
For all b and b, there exists an a in a such that f of a is equal to b. That's what I need to show. So let B be any element in B. How do I know that there is some element in F that will give me that function?
F of G of, well, G of f of a, we already showed can potentially just give you a,
G of F of,
well, there exists a number such that g of that number will give you a. So then if you have f of g of, or f of g of x.
Look at the first composition.
There exists a number.
So
This is what you're saying? There exists
some x in, or some a in a, such that g of f of a. I was going to say such that g of f of a, or g of f of. Would it be fair to say that g of f of a can equal some b, given the one-to-one relationship we saw before?
Yeah, but I need to know it's that b. I want to make sure that the b I'm choosing is not outside of the range of this thing.
Can you plug it into the other one?
Yeah, can you use the f of g equals in
Okay, so I would know that f of g. I would know that f of g is, if I plug in the b into f of g, the output is b, okay?
right in front of me?
By assumption, f of g of b must be b. But this means that f of g of b must be b. But what is g of b? But g of b is in a, right? G is a function that goes from b to a. So if I find g of some element here, it's going to be outputted in some element in a, right? So because I know f of g of b is b, because it's the identity function, then that means this guy is b, but that guy is just an element of a. Therefore, choose a equals g of b, and we have an a in a such that f of a equals b. How would I show that g is the inverse of f? I'll give you a hint. One, if that's one way you can show this. We know that they're going back and forth between the same sets. So all I just need to show is that I can flip the first and second coordinates, and everything should be fine. So how would I know that if, so that is, if f of a equals b, then it must be the case that g of b must give you back a. It must be able to reverse the relationship.
Do you have the right proof that? And then a common
Okay. Suppose AB is an element of f, so f of a equals b.
Since we know it's bijective.
We don't know it's bijective. Well, oh, yes, we do at this point. We know it's f is 1-to-1 and onto. Yeah. So you want to use that somehow?
Yeah.
Okay. Remember, ultimately, I want to say that g of b is equal to a.
use the G of
F. Okay.
Just plug both sides into G. This would mean that if I take G of this side, it's the same as taking G of that side because they're the same. And G of F is the identity on A. So if I'm taking some element that's in A, which is little a, G of F is just going to give me that guy back. Again, the moral of the story is you need to make sure you know all your definitions because those are telling you the things that you need to show, and you need to be able to use the assumptions that you're given in the problem. So odds are, and this is again a kind of, it's often difficult when you're practicing proofs in the first place to know when you're right, you know, because it's not like you can plug things into a calculator and check it, but it's very useful to know things like, well, if I don't use all the assumptions that were given, then I probably did something wrong. Right? The mere fact that we tell you, you have to assume something to make this true. If you can prove that true without even talking about those, you're probably missing something. So we're using the fact over and over that when we're taking the composition, we're getting the identity. We need to use that fact for our composition. So you need to know the definitions you need to prove, and you need to use the context that's given to you in order to prove that the definitions hold. So we didn't technically need the fact that F is bijective here. I don't know if you saw a way to use that to figure that out. Ultimately, we wanted to say something about G, so I'm not sure how you would jump from the fact some property of F and get over there. Here's another concrete example. And at this point, most of the proofs that I'm actually going through in class, they're proofs of this difficulty or test worthy. You know, if something is not too test worthy, I'll probably just skip it at this point. And leave it to the reader. So here, F goes from R minus 3 to R minus 5. X equals 5x over x minus 3. So did I actually do something with this example already?
It was a similar one.
It was a very similar one. The formula was slightly different, right?
Yeah.
Okay, so you should know a lot of this. It's a good thing to go over. A. Show F is bijective, which, since it's super similar to the other example, this is something that we should be able to get through pretty quickly. And B, find F inverse. Let's go through this quickly. A. How do you know that F is 1 to 1?
Suppose f of x is equal to f of y.
Assume f of x equals f of y. This means that 5x over x minus 3 is equal to 5y over y minus 3. This means you can cross multiply 5xy minus 15x is equal to 5xy minus 15y. This gives you that minus 15x equals minus 15y, which means that x equals y. F is onto. So let y be any element in the range. Choose x in the domain x equals this, then f of x equals f of blah is going to be equal to 5 times blah over blah minus 3, which is going to be equal to, and eventually I know I want to get y at the end here. So you can actually start to fill out a template, because at this point it's just going to be a beat by beat kind of thing. The thing is now we just need to know what goes inside of blah. And so you go to the side, and what are we going to do inside? Right, I know I want y to be equal to f of x. So now I'm going to try here to solve for what x has to be. This means that xy minus 3y equals 5x. This means that xy minus 5x equals 3y. This means that x equals 3y over y minus 5. This is okay since y is not 5. Also, you should be aware that x is not equal to 3, for assume it is, then we'd end up with 3y over y minus 5 equals 3, and then we get 3y equals 3y minus 15, and you get 0 equals minus 15, so that's absurd, and so this is the guy that we are looking for, and so I can come over here, and I can actually plug that in. So I'm going to choose f equals 3y over y minus 5. Plug in here 3y over y minus 5. Plug in here 3y over y minus 5, and 3y over y minus 5. And at this point, I'm just simplifying. Multiply this by y minus 5 over y minus 5. And here I would get 15y. On the bottom, I would get 3y minus 3 times y minus 5. That's going to give me 15y over 15, which is y. So f is bijective. Yeah.
I have a question on that thing again, I guess. Okay. Do you have to do that, like, that justification?
Which is
Say that when you're writing the proof and choosing the x value, isn't it assumed that you're choosing from your domain? So then, like, and then since it's not including the, like, do you need to show every?
Yes, you should. The reason being is that it seems silly that I'm doing it here because everything works out.
I can understand for why, but like for the 3, like, is that, should we just say it? Or, for clarity.
You can mention it here, although I probably wouldn't care. The thing is, if you don't do these checks, you can end up making a mistake in the situation where it's not a bijection, but you might think it is, right? So going through this painstaking process, if it's not a bijection, something here is going to break, and so you'll know that, okay, I shouldn't think of it as one. So yeah, it seems silly how things are going to work out here, but that's because we know ahead of time it's a bijection. Of course, everything's going to work out nicely. But in practice, you won't necessarily know ahead of time. Right? Sometimes a function is not given to you, right, which we're going to do in chapter 10. You have to create a function, and then you have to make sure it's bijective, which means ahead of time, you're just going to create it, because the thing is, because you're a human being, you can't see an infinite number of values going into something. So sometimes you compute a finite number of values, create a function that works for those finite number of values, but then you want to check that it works for everyone and it's bijective. It requires you going through and really checking every little minute detail. So yeah, a check seems silly in this case, but that's only because we know ahead of time it's bijective. Of course, everything's going to work out and look silly, but it's an important thing to check in the event that you're the one creating the function. And you might not know it's bijective to begin with. So here, f inverse of x is, you guess it's going to be this guy. So give me any function in the range, in the codomain, then this element is in the domain and will map to that number. And we can check that if I take f of f inverse as defined above, I will get the identity on B. And if I take f inverse of f of x, that is the identity on A, where this is the A and that's the B. Let's move on. A very important kind of function are permutations. Now when you get into abstract algebra, these guys are going to be a very fundamental set of objects, which you would call groups. I'm not going to tell you what a group is. They're a set of objects that when you pair them with an operation, we call them a group. And this is one of the fundamental group examples that you would see. Z mod n itself is also a group with addition, as we defined it. And so these are some of the most basic examples that you will use. And for those of you in my linear algebra class, we are dealing with things where we spoke about how you can take arbitrary vector spaces and you can somehow make them equivalent to Rn under certain conditions. And so what happens is groups can get really weird and crazy, but a lot of times we can somehow connect them to much simpler groups that we fully understand. Z mod n is such a group. It's one of those fundamental examples where it's easy to kind of, there are ever so often we can connect things to Z mod n so we know how they will work. This would be the next basic example. The set of permutations under composition is called the symmetric group. And they are really, it's a set of functions. So we're going to look at sets of functions here, and these are pretty much a set of bijections from a set to itself. Alpha. So I'm going to call a permutation alpha on A is a bijection from A to itself. Bijections from a set to itself is called permutations. And some of you might have done combinatorics or probability before, and so you know permutation. You probably understand it in another sense. Permutation is a rearrangement, but it turns out a rearrangement you can think of as a function. Right? So if you want to really condense the idea of rearranging something to some sort of concise mathematical concept, the best concept is a function from a set to itself. So what you can do is, you can think of all the elements being in a certain position, and when they map to someone else in that set, you can think of them changing positions with that element. And so you can think about a rearrangement as just a function from a set to itself, where the function is, you can think of it as assigning a new position to any given element. So, maybe I should mention that. We can think of this function as a rearrangement of the elements of A. So in a probability class, that's how they tell you what a permutation is. What's a permutation? Well, it's a rearrangement of the elements, right? So you can do things in any order, essentially. And you call that a permutation. And let me just give you maybe a slight example here. Let's say my A is 1, 2, 3. And I can even somehow sort of informally impose an order here, so I can think of 1 as the first element, 2 as the second element, 3 as the third element. I can think of them being in a position. But if I do a function from A to A, where I do something like alpha of 1 is equal to 3, alpha of 2 is equal to 1, and alpha of 3 would be equal to 2, what would happen is you realize this set A, which we originally thought of as 1, 2, 3, well now the 1 will be connected to the 3, the 2 will be connected to the 1, and the 3 would be connected to the 2. So if I again impose some artificial order here, now the 3 becomes the first guy, and the 1 becomes the second guy, and the 2 becomes the third guy. Right? So if I'm conceptualizing some sort of order here, a function from a set to itself can be a mix-up of this order. Right? And so you can kind of think of it as something that helps you change position, so you can think of it as a rearrangement. And that itself has all sorts of geometrical implications. So for example, if you have a triangle, and you can label this is the first vertex, this is the second vertex, this is the third vertex. Basically what you just did was you rearranged the 1 vertex now goes to the third vertex, the 3 goes to the 2, and the 2 went to the 1. So you can think of this as just a rotation of this triangle. So now the 1 would end up here, the 3 would end up here, and the 2 would end up here. It's the same triangle, it's just a rearrangement of the order of the vertices. And that's why the set of permutations is often called the symmetric group, because if you think of it in the geometric context, things will remain symmetric, you're just sort of moving guys around. So there are many like geometrical and process-oriented interpretations of such functions. We're not going to get into that. That's really things that you'll explore a lot in abstract algebra. I'm basically now just introducing it to you so that when you go to abstract algebra and your professors start talking about this, you'll kind of be able to hit the ground running. So I'll give you some more examples. I gave you some random things. So again, if A equals ABC, then if I look at alpha equals AABB, CC, and beta equals, I move the A to the B, I move B to the C, C moves to the A. These guys are permutations. So any function that is not a bijection is not a permutation. I didn't give a non-example, but
sorry, identity functions are permutations?
this would be the identity function. The identity function is a permutation. It's the most boring permutation there is. It doesn't change any position. So it doesn't rearrange anything. The identity function is the guy that's that, they're fine, just leave them there. So now let's talk about a notation. And again, in abstract algebra, you actually come up with a much more compact notation than this. But for now, especially with a few finite elements that we're going to be dealing with, the notation is to do this sort of thing. You would list the elements here. So the domain elements are listed at the top, and the guys that they are connected to are listed at the bottom. So you can do this. Whereas you can think of the data as this. So here are your domain elements. And these guys here below are the corresponding outputs. So you list all the domain elements at the top. If you want to move someone to another position, you just put their new position under the bottom, and this object here is called permutation. You think of it as a function that's rearranging the elements. Now let's look at the set of all permutations. Let's look at some ideas. Let A be the set 1, 2. List all possible permutations. I believe I also did for 3 lines. List all possible permutations. Okay, tell me a permutation. Tell me one of them. 1 and 2, and 1 goes to 1, 2 goes to 2. No change. Another permutation. So it always starts with 1 and 2 at the top.
2, 1.
You can do 2, 1. Okay, another permutation.
Can you have any more?
There are no more. Those are all. There were only 2. Here. 1, 2, 3. One permutation is to literally do nothing. Okay. 2. Another one.
3, 2, 1.
3, 2, 1. Sure.
1, 3, 2.
Are you guys randomly guessing things, or do you have like an algorithm in here? It's always good to come up with an algorithm here. I'm not sure if you guys have one, but okay, keep going.
2, 1, 3, and 2, 3, 1.
We have 2, 1, 3, and 2, 3, 1. Alright, so I'd like keep the first element and switch the order of these two. Then switch the first element, switch the order of those two, switch the first element, and switch the order of the other two. So that probably would be the process I would think here. Of course, with the larger numbers, this gets harder and harder. But for 3, it's not so bad. So I have 1, 2, 3. Do I have 1, 3, 2? We already have that, okay. So let's say I go to the ones where 2 is in the front. I have 2, 1, 3, and I have 2, 3, 1. What are the ones where 3 is in the front? I have 3, 1, 2. 3, 2, 1.
Yeah, I have that.
Okay. So what am I missing?
Isn't that all presentations?
So that is it. So let A be size n. how many permutations does n have? Right? Because you don't want to get into the situation of like what we're doing. Do we get all of them? Does A have? How would you be able to figure that out? It's going to be n factorial. Quick reason why.
For the first element, you have 3 choices. For the second element, well, actually, no. First element, you have n choices. For the second element, you have n minus 1, and so on.
Right. It's the same. It's pretty much the same argument that we had for bijection. Remember, we looked at the number of sets of bijection from a set to itself has to be n factorial for that same reasoning. You start connecting things one to one, such that once you pick the first element, you can't pick them again, right? So if you have n choices for the first guy, but then you have n minus 1 choices for the second guy, n minus 2 choices for the third guy, and so on and so forth. You end up with how many possible choices? N times n minus 1 times n minus 2, all the way down to 1. And so the answer is n factorial. So that's the same. So this guy here, we knew we got all of them because there are 2 factorial things here. This guy right here, there are 3 factorial things here, which is 3 times 2 equals 6. So I know that there are 6 total permutations on a set of size 3. There are 2 permutations on a set of size 2. There are, of course, there are 24 permutations on a set of size 4. So they start to grow really fast. N factorial grows really fast, grows faster than a polynomial, grows faster than any exponential. So you can get really big really fast. But it's a very important group to study anyway. So let A equals N. N in N, the set of all permutations on A is denoted. Does anyone know the notation?
There's a P, some kind of fancy P.
No. It's S subscript N. Where the S actually stands for symmetric. The name comes from the symmetric group, which is this geometric interpretation of, rearranging the vertices on some sort of geometric object. You'll really end up with something symmetric. You're just rotating the object into all possible. Rotating, reflecting, flipping, and doing things with the object. You'll always get a symmetric object, so it's called a symmetric group. It's called Sn. It's called the symmetric group. When you learn about what a group is, you realize that you always need to specify an operation with the sets. It's a symmetric group with the operation composition. At this point, if you don't know how the operation fits into it, that's fine. You don't need to know. We're not going that deep. But you just need to know what it is and what the set of all possible permutations are. So you'll know that S is a set of functions, it's a set of rearrangements. So we know, for example, that S2 is just the set of alpha 1 and alpha 2, where your alpha 1 is just the function that maps 1 to 1 and 2 to 2, and alpha 2 is the function that maps 1 to 2 and 2 to 1. Right? And it's the set of these things. If you take all these possible functions, throw them in a set, you get what's the set Sn, which is the symmetric group of n elements. And for those of you in linear algebra, this should probably be a little clearer, because when we define vector spaces, you would realize that it wasn't just important about the sets that we were talking about, it was important what operations, what addition meant, and what scalar multiplication meant. In the same way, when you were looking at something as a group, there is a single operation that's important, and it needs to fulfill certain properties. And Sn will fulfill those properties when you take the operation of composition. Is composition the next thing we're going to talk about?
Like, do they have any numbers?
Hmm?
Do they have any numbers, like actual functions themselves? Like
They're thought of as numbers because any finite set of things, you can replace them with a number anyway. So A could be the set A, B, but then alpha 1 would just take A to A, B to B, and alpha 2 would take A to B and B to A. So in principle, the idea would be exactly the same. So we usually just think of them as being numbers, but they don't technically have to be. They could be coordinates in the geometric sense. So we're looking at plugging vertices on a plane. These guys are actually representing vertices, but we still can call them the first vertice and the second vertice and the third vertice. Right? So any other finite set of things that we have, we can make it somehow equivalent to a set of numbers, set of natural numbers, because we're just counting how many objects there are. Remember, since Sn contains bijections, we can compose its elements and find inverses, etc. Right, so these guys are all functions and they're bijective functions. So there's a notion of taking the inverse of each element and things of that sort. And the inverse will be an inverse in the strictest sense, meaning that if I have one guy who's an inverse of another guy, if I compose them, I should get the identity permutations, the permutation that does nothing, right, by previous theory. So let's actually do some examples of that. For A equals 1, 2, 3, find so I said here alpha 3 composed with alpha 6. I think I wanted to take the order there. Alpha 3 composed with alpha 6. I want you to find the inverse of alpha 4. From before, what was alpha 3, what was alpha 6, and what was alpha 4?
We had 1, 3, 2.
We had 1, 3, 2 here.
2, 3, 1 for the next.
We had 2, 3, 1 here.
And that one was a 3, 1, 2.
And this was 3, 1, 2. Okay, so let's actually do these operations. A. So if I take alpha 3 and I compose with alpha 6, that is just the same as saying taking 1, 2, 3, composing it with this 1, 2, 3. Alpha 3 was 1, 3, 2. This guy was 2, 3, 1. This guy, okay. So I just rewrote this. I did nothing because I just wanted to showcase we usually don't write the compose sign. Sort of like how with matrix multiplication, we really thought of it as a composition of linear transformations, but we don't write it when we're writing matrix multiplication, we just write it as a multiplication. The same thing happens for symmetric groups. Okay, so that means I have 1 through 2, 2, 3, 1. Now the composition works just as how you would think. You apply the guy that's on the right side first, then you apply the guy that's on the left. So what would that give us? So I know it's just going to be another bijection from the set 1, 2, 3 to something else. But what comes down here is the question. So what happens is you're going to, again, think of this as a function that moves 1 to 2, and then you're going to plug that into this function that's going to move that number to something else. So you start here, okay, 1 goes to 2, and then when you plug it into that other function, 2 goes to 3. So ultimately, at the end of its journey, 1 ends up at 3. So I will put the number 3 here.
And we do the ordered pair way too.
You could, but this is the typical notation. So 2 goes to 3. And the thing is, this notation, you can actually compress them. And so thinking about it this way allows you to compress it in convenient ways later on. So we usually write it this way. Whereas the sets of coordinates don't have the same appeal. Similarly here, I take 2 goes to 3. Then of course I would plug that into where 3 is. And then 3 goes to 2. So ultimately 2 goes to 3, plug it in here, 3 goes to 2. So 2 goes to itself. And so we have 2. And you continue the process. 3 would go to 1. And now you have to figure out, when I plug that into the next function, 1 goes to 1. So ultimately 3 ends up at 1. Which, by the way, at this last point, 1 was the only guy left anyway. So technically, if you do all of this except one guy, that has to be the remaining guy. So I didn't technically have to go through this process, but it was necessary. So I can compose these two functions and I can get another function. And the nice thing about this, I mean, technically it's not Marcellus, but you can actually compress this object to look like a vector. In the sense that you can say start at 1, 1 goes to 3, and you realize that 3 goes back to 1, so you can stop there. 2 goes to itself, so you multiply by 2, you'd obtain the same thing. But guys that are numbers by themselves, they're essentially a mini identity function, so you can ignore them and just write this as the vector 1, 3. So if I thought of composing two sets of coordinates and I get a huge list of sets of coordinates, it's hard to do that kind of compression. So this huge object here, I can express it as this, just a 2D vector. And it turns out you can think of, even when you get larger, it turns out that there's a theorem that tells you you can always compress one of these guys into just a product of 2D vectors of this form. And then you can talk about the properties, whether there's an even number of them in the list or an odd number of them. And you get a lot of nice things out of that. So this notation allows for some compression. So for this one, for example, you have 1 goes to 1, so that ends the chain. 2 goes to 3, and 3 goes back to 2. So this guy I can think of just as, I don't want to say a vector, but that's what it looks like, so I'm just going to use that language now. Here you can write this as 1 goes to 2, and 2 goes to 3. And so that's guys a 3, 1, but again, you'd be able to write this as a product of 2. This one you have 1 goes to 3, 3 goes to 2. So there are shorthands for these objects if you don't like writing them down. But I don't think our textbook goes through that and all of the results. Finally, let's finally get to part B, the inverse of alpha 4. Remember, this was 1, 2, 3, 3, 2, 1. Well, 3, 1, 2. So what is alpha 4 inverse. Right? Remember, alpha 4 inverse is the guy that turns all the pairs backwards. So basically, you can think of it as, it's now the range you think of as the domain, and the domain becomes the range. So there are a couple steps that you can do to make this easier on yourself. What you can do first is flip the domain and range. So here, I just take this and turn it upside down. So 3, 1, 2 goes at the top, 1, 2, 3 goes at the bottom. And then now the second step would be to rearrange so top row is in the natural order. So now I'm going to just start moving columns around, rearrange the columns. So the top row is in the natural order. So the column 1, 2, I move to the front because that would make the 1 in the top. And then the next thing to be in order would be 2, 3. The next thing to be in order would be 3, 1. So this column here, because the 1 is on top, I move it here. This guy here, the 2 is on top, move it there. This guy here, the 3 is on top, move it there. And I get this permutation. Notice here that alpha 4 inverse ends up being alpha 6. Which is one of the properties of a group. The inverse of every element is another element in the group. So your book doesn't go very deep into this, but in an abstract algebra course, you'll start to do a lot with these guys, including more notations and how to think about them in terms of these compressed notations. And the fact that there are groups with respect to the composition, and that gives you a lot of consequences. So a group is just another kind of set operation pairing, kind of like a vector space is a set operation. And that ends chapter 9. We're going to start off chapter 10, just get some definitions out of the way to get on some nice footing, and then we'll continue with that on Tuesday. Chapter 10, Cardinalities of Sets. Remember, cardinality is a notion of the size of a set. How big something is, how many elements it has. Of course, if this is a finite element, then you can describe the cardinality with a natural number. You can say it has 5 elements or something like that. But infinite sets can get pretty tricky because you won't always be able to describe it by something as small as the set of natural numbers. So let's do something. A set A is called finite if A is the empty set or the cardinality of A, the size of A, which we introduced before, is n for some n in n. The set that is not finite is called infinite. So, example, A equals 1, 2, 3 is finite A equals the set n itself is infinite. So is the set of real numbers, so is the set of integers, so is the set of rational numbers. We have seen many examples of infinite sets, but we're going to look at them in a way that probably you've never looked at them before. We're going to want to be able to talk about the size of these guys. So that's the definition of a finite set, and by contrast, we define what it means to be an infinite set. If the set is non-empty, and you cannot describe its cardinality using a natural number, we will call the set infinite. There are, as we will see, many varieties here of varying sizes. And eventually we'll get to, well, we won't get to this stage, but maybe if you get to like a set theory, you get to the stage where even the notion of size becomes silly because things get so big that even infinity doesn't describe it as a size. So you can get so big so that talking about size becomes like meaningless. Like, what do you even mean? How big it is? Don't you understand how big it is? Like, no, you can't understand how big it is. It's too big to understand how big it is. We're not going there. We're going to deal with relatively small sets like the real numbers. They're very tiny baby sets. So now we want to, how can we talk? This is the main goal of chapter 10. How can we talk about the cardinalities of infinite sets? Right? If A is infinite, then the size of A equals what the heck? Like, what does it mean now to actually write that notation down? So let's start with an idea on counting. Now, those of you who are in my linear algebra class, you've heard me do this spiel before. I'm going to do a much more condensed version of it. Because you guys are used to thinking of things abstractly at this point, I think. Is the idea of measuring size without counting. Not in a combinatorial sense, because those of you who did combinatorials will realize that you tend to be counting finite things all the time. I.e., we're going to look at the sense of counting by comparing things. Because usually that's the point of counting anyway, right? When you count something and you say there are 4 of these things and there are 5 of those things, it's really a comparison. You want to be able to say, oh, there are more things over here than there are over there, right? So writing down the symbol 4 is only useful if there are other symbols out there to compare it to, right? You know that this symbol represents something that's smaller numerically than that symbol, and vice versa. And you know that the symbol 7 is something that's bigger than this, but it's smaller than that. It's somewhere in the middle, right? You can use these notions of sizes to compare things. That's kind of the whole point. And so sometimes we want to know about counting, but we count by comparison, by measuring things. So for example, and I'll give you guys the same example. So for those of you who are in 346, tough luck, you're going to have to hear this again. If I wanted to, now this is possible, but the idea you want to extrapolate it to the infinite case where it wouldn't be possible for me to do this. But if I wanted to count, for example, by comparison, the number of chairs in the room compared to the number of students, now technically I could count it and just write those down. But let's pretend that I don't want to do that or I'm too lazy, which I am, right? One thing I can do though is I would be able to compare the sizes. I would be able to say there are more students than there are chairs, or there are more chairs than there are students, or there are exactly the same number of students as there are chairs, right? I would be able to make this comparison without actually counting people. And how do you think we can do that? No one in 346 answered. How would I be able to tell that without specifically counting you guys? Are there more students here than there are chairs? What's the answer?
Yeah.
No.
No.
Right, how do you know that? Did you actually specifically just count the chairs and students? What did you notice?
Compare.
They're empty chairs. Just glance.
They're empty chairs. What does that mean? Right? You have someone sitting in a chair, what you can think of is that person is assigned to that chair, right? Basically, I can kind of rethink of this in the sense of functions. Think of the set of students as the domain, think of the set of chairs as the range. If someone is sitting in a chair, it means that that student was assigned to that chair. I just created a rule that connected the set of students to the set of chairs. Now, what an empty chair means is that there is an element in the codomain that was not assigned from an element in the domain. Meaning that an empty chair represents something that's in the codomain but is not in the range. Right? So the fact that you see an empty chair is you saying, oh, this function is not onto. There are elements in the codomain that were not in the range. So the fact that I can create a one-to-one function between students and chairs, but the function is not onto, means that there are more chairs than there are students, right? So I can compare them without actually specifically counting them. Conversely, let's say I had too many students, right? I'd be able to assign a student to every chair. There's still a bunch of students standing around. Oh, I tried to create a one-to-one function, but I filled up the codomain before all the domain elements were assigned. Now, if I forced everyone get on a desk, I don't care how you do it. People are sitting on top of desks, people sitting in each other's laps. Now I would have created a function where I have a desk, but it has more than one domain element mapping to that desk. In other words, I've created a function that's onto but not one-to-one. Whenever that is possible, that means the domain is bigger than the codomain, right? I have too many domain elements compared to the range elements. The sweet spot is when you know two things are the same size, is when all the chairs are filled, there are no students left over, there are no empty chairs. When you're able to create a one-to-one function that is also onto, something that's one-to-one and onto at the same time, every desk has one student and only one student, there are no desks without students, there are no students without desks. That means they're the same number of students as there are desks, right? So without specifically assigning things a numerical value, some number that I know on the number line, I can still tell where things would be in relation to each other. And so I can kind of create a number system based on comparison. And I can kind of create that number system using functions, right? One of the many ways you can use functions. So that's kind of what we're going to be doing in this chapter. We're going to be measuring the notion of size when we're not able to assign things numbers. Like we can't assign a number of real numbers. I can't say there are 7 real numbers in all of reality. That's not true. And any number I pick on the real number line will be too small to describe how many numbers there are in that set. So I have to find some other way of describing size. And the size, the other way is comparison via functions. Okay? So that gives us our next definition. Sets A and B are called numerically equivalent if there is a bijective function f from A to B. And of course, if we know there's a bijective function from A to B, there's also a bijective function from B to A, namely the inverse is one such function. There are, of course, other such functions, but there's at least one for sure. So these guys are called numerically equivalent. In this case, we write the size of A is the same as the size of B. Right? So while I might not know exactly what number might describe these guys, I might be in a situation where assigning them a number doesn't even make sense, but I can tell that they have the same number, the same amount of elements by this criteria, the kind of what I illustrated with the students and the chairs, right? Create a function between the two sets. If you can create it in such a way that is one-to-one and onto, they have the same number of things in them. and we call them numerically equivalent. So we say their cardinalities are the same. Right? So this is the idea that we're going to be using with counting now, especially in the infinite case. In the finite case, it's easy. Count it how you always did, 1, 2, 3. Maybe you use arguments from combinatorics if your set is sophisticated, created in some sort of sophisticated rule, like the number of ways you can draw a queen out of a deck of cards and blah, blah, blah. Then you can't really count 1, 2, 3. That's going to be annoying. There's a process that you can go through. That's combinatorics, but that only deals with the finite case. We want to talk about even infinite cases where we can actually talk about comparing things, and we do that via functions. And so, as far as we're concerned now, I can only say that two sets have the same cardinality if I can find some function that connects these two sets in a bijective way. So when people, and some of you have heard this before, when people say, you know what, there are more real numbers than there are integers, you're like, really? Who counted both of these things and came up with that conclusion? Like, seriously, show me the guy who wrote everyone down, wrote down all the integers, wrote down all the real numbers, and said, you know what, this book is bigger than that. No one has done it. How we know that is by this idea. It turns out that we cannot create a bijective function between the real numbers and the integers. It turns out we can use up all the integers and still have things left over. There will still be empty chairs. We're going to prove that, by the way, but not now. Right now, we're just learning. So right now, let's mention something here. And now we're going to explore this idea that we've seen before, or at least I mentioned before, the notion that you can talk about size in various different ways, and they're somehow all mean the same thing. So I want to show you that our use of the word equivalent here is not ambiguous, and that numerical equivalence is something that we can actually talk about. I can talk about all sets of a certain cardinality that are equivalent somehow in a numerical sense. Kind of how I can say all of these symbols, they are equivalent in the numerical sense. They might look different, they might have different elements, they might be composed different, but they're all the same when you're talking about size. In the same way, I want to prove to you that this relationship is the same when I'm talking about size. So, define a relation on sets such that A relates to B if the size of A equals the size of B. By this definition, then this is an equivalence relation. So we are going to be able to talk about size, but you are going to realize that there are certain equivalence relations. For example, we are going to end up being able to prove that the size of the natural numbers is the same as the size of the integers. There are a different number of elements, they look the same. It's probably not intuitive, because intuitively you would think that the natural numbers is about half the amount of things because there are no negatives, but no, it's exactly the same amount of things. As numerically speaking, these two sets are equivalent. If you're talking about how many elements are in them, it's the same. They're in the same category, they're in the same thing. Right, so that's what we want to actually discuss here. This forms an equivalence relation. Let's do a proof of that. Of course, in the empty case, it's easy. because everything is fulfilled trivially through all the rules. If everyone's empty, then yes, they're the same. So assume all the sets are non-numerical. Let A be a set. How do I know that A would relate to itself? Then A equals A since the identity function. The identity function on A from A to A is a bijection. So A relates to A. A relates to itself. Therefore, this relation is a reflexive relation. So that was the first point. Second point. Suppose A equals B. Then that means there exists some function from A to B that is a bijection. Then, how do I know this is symmetric? Then F inverse from B to A is a bijection from B to A. And so that means that the size of B must be the size of A as well, and A relates to B will imply that B relates to A under this relation. Because we can use the inverse, which we know exists. We proved that earlier today. How do we know it's transitive? Suppose A relates to B and B relates to C. Okay. Then there exists F from A to B that's bijective, and there exists a G from B to C that is bijective. How do I know that A relates to C?
Composition.
Composition. Then this means that G of F goes from A to C is bijective. So if A and B are the same size and B and C are the same size, then A and C will be the same size. We have transitivity, right? We proved that this was bijective in the last class, I think, right? So the composition of two bijective functions is itself bijective. And so the identity function will map a set from A to itself, prove that A is numerically equivalent to itself. If A is numerically equivalent to B, then B must be numerically equivalent to A using the fact that every bijection has an inverse and the inverse will fulfill that definition. If A is numerically equivalent to B and B is numerically equivalent to C, then A is numerically equivalent to C via the composition function. And that is bijective when its individual functions are bijective. So this is an equivalence class that we can talk about. We can talk about sets of a certain cardinality. So we can talk about sets that are finite. Those are of one class. They are all somehow equivalent. And we can talk about infinite sets, but that's a little bit trickier because we'll see that there are many notions here for equivalence in terms of infinite sets. Here's the first class of infinite sets. A set A is called innumerable if the size of A is equal to the size of N. know is an infinite set. I will classify any set that has the same number of elements as n. We call these the denumerable sets. This is one classification of infinite sets. It's the smallest infinity. So, did I give an example here, or did I just define countable? Let me just define countable here, then maybe I'll talk about denumerable. A set A is called countable if A is finite, which means either it's an infinite set or its cardinality can be described by a natural number or denumerable. So the word countable captures every cardinality from the finite case up to the infinite case that is up to size n. We're out of time. We'll talk a little bit more about this later. Some consequences of being countable. And then we'll start to actually measure sets. So the next class will show that n and z and q are all the same. We'll show that r is bigger than n and all that stuff, all that fun stuff. I'll see you guys on Tuesday. So the homework for chapter 9 will also be due on Tuesday.